This video will be solving Leetcode problem number 70, climbing stairs. So the problem is we are climbing a staircase and it takes n steps to reach the top of the staircase, and we can either climb one or two steps at a time, and we have to figure out how many distinct ways we have to climb the top. There are some examples given. So if n is equal to 2, then we have two distinct ways. We can take two single steps, or we can directly take two steps and reach the top. And if n is equal to 3, then we can take single steps, or we can take one and two steps, or we can take two steps and one step. So we can see this diagram to understand the problem better. So if n equal to 1 from the plane, we can only option is to take one step, and we have only one way of doing it. And as we saw, if n equal to 2, we can take one step and then one step, or we can directly jump to the top using two steps. So we have two ways. Taking some bigger example and representing this into a tree, binary tree. So if n is equal to 5, if we take one step, we are left with 4 more steps, or if we take 2 steps from 5, we are left with 3 more steps. And similarly it goes on from 4. Again we can take one step or two steps. So this way we can represent the problem using a binary tree also. So to solve this problem, we can simulate this tree into our code. So what we can do is we can write a recursive solution to it, because whenever we have tree and we have multiple options from each step, the easiest and intuitive solution is to do it recursively. So first we'll have a base condition if n equal to 3, because if n equal to 1 or 2, we know the answer and will be equal to n itself, because if n is equal to 1, we have only one way, and if n equal to 2, we have only two ways to do it. For n equal to 3 also we have 3, but it's fine, we can take less than equal to 3. And then we can do climb stairs. We can call the same function but with lesser number of stairs. So self dot and we can take two steps. So this is our solution to this problem. We'll get into the complexity. Let's first test this. So take these two examples, or rather add more. 1 2 3 4 5. And we also see that the input is from 1 to 45. Yeah, it got accepted. So let's submit this problem. Time limit exceeded for input 38, and we have input range till 45. So so generally when bigger test case fails, the problem is with the complexity. Our solution is not optimal. However, our solution is correct but not optimal. So we'll go back to our previous diagram. In this, we'll try to figure out what is the complexity of our solution that we have done. So this is so if we have n equal to 5, our height of this tree turns out to be 4, because our 2 and 1 becomes the base case, and then we are not recursing further. That's why our height of the tree is 5, and if we generalize this, it will be n minus 1. If n is the number of stairs, our height will be n minus 1. And in a binary tree, we know that if height of the tree, if the height of the balanced tree is n, then the total number of nodes in that tree would be 2 raised to power n. So that's why the time complexity of this solution is 2 raised to power n, which is exponential. That's why it is not accepting, and for 38 it is giving time limit exceeded. To optimize this, what we can do is we can cache the results. So here in this diagram itself, we see that 3 has been repeated twice. If the tree is bigger, if our number is bigger, so it will be repeated many number of times. Although we see that 2, 1, and these are also repeated, but for these things we are not calculating anything. We are just returning from the base case itself, and for any number higher than 2 we are recursing. So what we can do is we can cache the results that we have been which we have already calculated, and then use that result whenever we can counter this. So for this we can use a simple hash map in any language, but in Python we have LRU cache in func tools, so I'll be using that from hash, and then I can cache this and use this. And it also accepts a parameter. Then if I submit this, yeah, it works. I'll test all the cases. Yeah, it works, and we are faster than 87% of the total Python 3 submission, so our solution is correct. Cache, our time complexity reduces to order of n, and is the number of states that we are given with, because now I am not recomputing for the same value of n. So I compute for 5, then I compute for 4, then I compute for 3, and again if I encounter 3, the result will be returned using the cache. So we are not computing for the same input again. So that's why our time complexity is order of n, and space complexity is also order of n, because we are using this cache, which will also take order of n space, and also this is a recursive solution, so recursion stack also takes order of n space. So this was the top down approach. So in DP we have multiple approaches to solve a problem. So this was the first one, top down approach. We can also solve the same problem using bottom up. So in that case we take a DP table, and then we keep on filling this the table, and ultimately at the end we have the solution. So we can update the solution itself. So we don't need this from tools. Base case remains same. So we'll take dp equal to 0 for of size n plus 1, and we'll fill in the base case. dp of if n equal to 1. So we are not using the zeroth index, we'll be using 1 to n. So if number of states equal to 1, then we have one distinct ways. If it is equal to 2, we have two distinct ways. Now we have to loop from 3 to n plus 1. Remember, we are using n also, nth index also. That's why this loops from. v minus 1 and dp of v minus 2. Then we'll be returning dp of v. So this should be done. So this line comes from the recursive solution itself. Therein we did n minus 1 plus n minus 2. We need to calculate the previous result, and then we'll get the value of the current input. That's why we are using this, and yeah, base case, and then at the nth index we'll get the result. Let me submit this. Yeah, this is submitted, and the time and space complexity remains the same, because here it's clear that time complexity is of the order of n and space complexity is order of n, because we are using dp and filling all the values to it. Optimization that we can do in terms of space complexity. So we see that in this statement we are only dependent on the last two states. We are not assessing any older value from the dp. That's why this can be solved using two variables also, rather than keeping all the solutions into a dp table. So that's the idea, and we'll be removing this dp table and using two variables only. So let's remove these things, and let's call variables as away, which is one away from our current value of n, and away 2, which is 2 away from our current value of n. So these are same as our base cases, and from here res equal to n. So let's initialize some value to it, and this is because if our input is 1 and 2, we won't get into this loop, and our solution will be equal to n. If n equal to 1, then number of distinct ways is 1, and for 2 also it is 2, and this will be equal to away plus away 2, and we has to update the values of away and away 2 also. Now away equals to away 2, and away 2 equals to my current solution, which is res, and here I'll remove this and return the value of res. We also note that now we don't need this additional condition, because if my n is less than 3, it won't go into the loop and it will return. That's why this condition is not required. It will be handled automatically. But in case of dp table, we needed this because we were accessing dp of 2. So if our input is 1, it was failing. That's why that additional condition was required. This we can remove, and then we'll submit the solution. Yeah, great. So time complexity remains same, it is order of n, but space complexity becomes order of 1, because we are not taking any array or any additional space which is proportional to n. We are always using two variables, and that's why we are using constant space. So the space complexity is order of 1 or constant. So that's it for this video. See you in the next video. Thank you.